Hello and welcome. My name is Albert Zeyer, and today I present my PhD thesis with the title Neural Network-Based Modeling and Architectures for Automatic Speech Recognition and Machine Translation. So setting is as follows. We have given some input sequence and then we have some model, usually a neural network, and we want to get some output sequence. The input sequence are usually audio features, characters or words, and the output sequence are also characters or words. And the task we focus on are automatic speech recognition, ASR, where we have given audio and we want to get out text, and we measure the word error rate, where lower is better. And another task is machine translation, where we have given text in one language and we want to translate it into text in another language. And we measure the bilingual evaluation understudy, bleu, where higher is better. So the scientific questions we want to investigate here. First of all, we want to improve state of the art for speech recognition and translation. It's the overall goal. Then we want to study what is the best type of neural network model. There we compare, for example, feed-forward network versus long short-term memory, LSTM, and others. We study offline versus online streaming capability and the influence of individual neural components. Then we study what is the best sequence-to-sequence architecture. There's, for example, the hybrid neural network in Markov model versus attention-based encoder-decoder models and others. And then we want to investigate more into the monotonicity for attention-based encoder-decoder models. And we highlight that this is an orthogonal question to the neural network model. All kinds of neural network models can be used in any sequence-to-sequence architecture. Further, we study the best training strategy. There's a training criteria, pre-training, regularization, data augmentation, and many other things. Again, this is orthogonal to the other questions. Another thing we studied more into detail was the full sum from scratch training, and then a better understanding of training behavior, model behavior. And finally, this was a big part of this work, is the software framework. And we wanted to come up with common recipes, which is now also used by a lot of people from the group. So that was the introduction. Now to the first chapter on neural network models. So the starting point of the PhD thesis in 2014 was the feed-forward network. This was back then state of the art. Such network does not have any context inside the neural network across the frames. The only context it has is through an input window. Then the LSTM, the original paper already was from the 90s. This is a recurrent neural network with gating. That means it now has some context. It usually does a recursion, which goes one direction in time, usually forward. But when you do offline recognition, you can also combine forward and backward direction, and you get the bidirectional LSTMs. And we see that these are also much better in performance. Otherwise, when you only go forward, for example, for online streaming, this is called a unidirectional LSTM. To get to some results, here for speech recognition, for hybrid neural network model on two data sets, and this compares it to the best feed-forward network we had at that point in time in our group, and this is quite a big improvement over that. So we see that BLSTM drastically outperforms the feed-forward network. So the scientific contribution is implementation of all of that, lots of investigations to really make it work for speech recognition, because this was non-trivial. And then we have code and recipes are widely used now among our group. So starting from that point in time, it became the new baseline for all our speech recognition models. Further extensions we made to the LSTM. I mentioned that the unidirectional performs much worse than the bidirectional. But here we investigate how you can make use of the bidirectional LSTM still for online streaming. And this turned out to be quite successful. So this is used now in production, and it mostly covers the offline performance, the methods we present here. Another model extension was the layer normalization in LSTMs, the layer-normalized LSTM. This gets to faster convergence, more stable training, and also improved word error rate. Okay, another model is a transformer model, originally from this paper, Attention is All You Need. This was originally introduced as an attention-based encoder-decoder model. However, nowadays the term transformer often refers to the structure of the neural model. Most importantly, the self-attention. So it has several neural components, most importantly self-attention. Then there's also cross-attention, but only for encoder-decoder. Residual connections, layer normalization, and feed-forward and modules. And the point is that this is quite simple, actually, as a model. Here are some comparisons of an LSTM to a transformer attention-based encoder-decoder model for speech recognition. We collect here the training. So on the x-axis you have the training time, and on the y-axis you have the word array. And the blue dots are transformer models, and the red dots are LSTM models. And what you see, or what's interesting, is of course the Pareto front, where you consistently see that there's mostly the transformer. So it means that for any given word array, the transformer gets there much faster. Also, another thing you see, overall, the very best model, it's very similar. So in this case, LSTM was still slightly better, but very similar actually. Also nowadays, we can say the conformer model, it was yet another improvement over the transformer. It's now clearly better than the LSTM. But the main point here is transformer trains actually much faster. So scientific contribution are the transformer for speech recognition, comparison to LSTM, and the code and recipes are widely used now. For language modeling, again, we have the case that LSTM was state of the art before there was a transformer. So we compared them. Here to just summarize, the transformer in this case, the language model outperforms the LSTM consistently across data sets. Again, to highlight, it trains much faster, which effectively then also allows you to train longer and also to train bigger models. So the scientific contribution are the transformer language models, which got us here really good state-of-the-art results on Nubi speech. And we also compared it to LSTM. And again, the code and the recipes are widely used now. To conclude this chapter, here are relative improvements we see due to several changes. First of all, the change due to the introduction of neural networks. Before that, we had Gaussian mixtures. This was a really huge jump in performance. But then the change from feed-forward to LSTM also got us quite big improvements. Further improvements were a bit less, but still nice. And also the more recent trend is maybe to actually just scale these models up and use more training data. Okay, this gets us to the next chapter, sequence architecture. The goal is that we want to model the probability of the output sequence given the input sequence. So example architectures are the hybrid neural network hidden Markov model, attention-based encoder-decoder model, or the transducer model, and a couple of others. Tasks are speech recognition, translation, but in general any sequence-to-sequence task. There are several aspects on these architectures, like what output label do you use actually here for the A? There could be phonemes, the characters, subwords, and others. Then there's often the term end-to-end, but we say this is kind of a loose term. Often it means that you use characters or subword units, and often it also means that the training procedure is simple in some way, and as well as the recognition procedure. As we mentioned before, this can make use of any neural model like BLSTM or transformer, so that's why it's orthogonal. Then there's the concept of an alignment, and you can have monotonicity or not, and the model could be online capable or not. So the attention-based encoder-decoder model, this was the first encoder-decoder model without attention was already from 2013. Then with attention from 2015, and this got very soon very good results for translation, became basically the new standard model for translation. Attention, this the same model then it was very generic, could be used for any sequence. The sequence task was then applied for speech recognition, but it took a bit to really get good results. So one very popular paper is the spec augment paper, which is a very simple data augmentation, and this got really, really good state-of-the-art results. So our own work here in 2018, we had some first publication where we got very good state-of-the-art results and for translation. And then we also had very good results in LibreSpeech for speech recognition. To be fair, LibreSpeech at that point in time was not so competitive. So, yeah. The model looks like that. So you have the encoder, which operates on the input sequence. There are multiple layers of something, in this case BLSTM here. For speech recognition specifically, you usually have downsampling. Here it's via time max pooling. Then the decoder gets as input the previous labels, so it has the label context. It should predict the probability of the next label. And via the attention mechanism, it has access to the encoder output. So the attention in every decoder step attends to the encoder output. In formulas, it looks like that. The probability of the sequence, you get the product over the output steps. This is just the softmax and then some very simple MLP, and you combine all the information from the decoder. And this C here, that's the attention context vector, and this is just a weighted sum over the encoder outputs. So the H is the encoder output, and the alphas, these are the attention weights. And this is normalized, so you have a softmax here, and the E is then the attention energies. And here we use some very simple MLP where we combine the decoder state and the encoder output. And the decoder, could be anything. So for the attention mechanism, there are multiple variants. You can do most common are MLP attention, as we see here, or also dot attention. One thing to note is that the attention is global. So in every decoder step, you access all of the encoders. This is what we mean by global. And this implies that you get OS times T time complexity, which is bad. This does not scale well to very long sequences. And also, this is not necessarily monotonic. So for translation, it does not need or should not be monotonic. But for speech recognition, this is maybe too much freedom for the model. So this gets us the motivation for the next model, where first of all, we want to introduce monotonicity for speech recognition specifically. We want to be able to do online streaming, and we also want to have an efficient model, so get rid of this time complexity which we've seen before, and to generalize to long sequences. We know that attention models do not generalize well to long sequences. An early own work on this was did local windowed attention variant, where we just used the local window and a couple of heuristics to get to the position. This works okay, but there's some small degradation. And then here we now introduce a more principled approach. We introduce a latent variable for the position or segment boundary. So it's a T here. And then it's similar as before. You have the product of the output steps. And this is now being split up into the model for the T. And this is what we call the length model, or also duration model. And then here we have the label model as before. It's also very similar as to before. However, this also has now additional the T, which we can use. So we compared 3 variants here. The T can be a position in the encoder output. So then this is usually the hard attention, or this is how it's called hard attention in the literature. This just uses one single frame from the encoder output. Another variant is that we make a local soft attention window around this position, T, or we can also interpret the T as segment boundaries and then use the local soft attention inside such a segment. So here are some results. We compared to the global soft attention case, and I have here the 3 variants. I just summarize that. So the local windowed attention variant performs best overall from these variants. However, compared to the global soft attention, it's not necessarily much better. It's actually very similar. So we get to the same performance, but also training was quite tricky. To get to these results, we needed lots of tricks and training schedules to get it to work. So contributions here are novel models, implementation of this extended search. So we need to search over the latent variable. We also do that in training, and then of course also in recognition. Now we get to another model with very similar motivations. So we want to have monotonicity, online streaming, efficiency. We want to generalize the long sequences. And we want to have a time synchronous model. So that means, because for online streaming, we usually do time synchronous decoding. And we want that our model nicely fits into this framework. So this model is a strict generalization and extension from the RNN transducer and also the recurrent neural aligner. These models usually introduce blank label to describe the forward transition. So for the alignment, there are these two variants. The original transduce RNN used this scheme, where only the blank moves forward in time and all the other labels stay in the same time frame. Whereas the RNA topology looks like that. Every output from the model gets you one forward in time. So this is conceptually simpler. And also now here we focus on this one, although in the thesis we did direct comparisons between both. So this is our model now. We introduce here the fast RNN and the slow RNN, where the fast RNN runs every time frame, and the slow RNN only runs when there's a non-blank output label. And so this is now the extended model, and this reduces to the RNN-T by just replacing the fast RNN with the feed-forward network, and to drop the connection from encoder to slow RNN, this connection here. Then this is exactly the same model as the RNN-T model. It also reduces to RNA by just dropping the slow RNN. Then it's exactly the RNA model. So this allows us now to do direct comparisons between those three kinds. And here are the results. We see that this extended variant performs best. The RNA comes close. The RNN-T is a bit worse. So further, we can see that there's actually we don't need the blank explicitly, but we can have a separate transition model. And this can be equally expressive. We can see that one can be reformulated into each other. So it means, same expressiveness. But it's a different kind of modeling. And when we compare them, we see that the separate transition model performs better in our case. And this gets us to the next point, the equivalence, or again, equally expressiveness to segmental models. We can reformulate segment one into the other, while keeping exactly the same probabilities for the sequence. In that case, when you already separated the transition model, so there's no blank anymore, then the label model just stays the same for this reformulation. But the transition model, this is the main idea here, can actually be reformulated into the length model and vice versa. This gives you this equivalence. So scientific contribution is a novel, generalized, and extended transducer model, comparisons to other models, and lots of ablation studies, and this equivalence. Okay, to conclude this chapter on sequence-to-sequence architectures, we try to make it as fair as possible, so all use here 6-layer BLSTM encoder, no speaker adaptation, no sequence training. However, so this is difficult to compare. So this reflects one point in time from our group where we collected the best results we had. But this is really constantly changing, and it's hard to make fair direct comparison because each of them gets further improvements and then some other model becomes the best overall model. So in this case here, the attention model was the best, maybe because this was trained longest. But then here we also have a direct comparison to to the transducer between attention, and we see that the transducer is better than attention here. So yeah, my conclusion from this is that it's still not conclusive, and there's really a lot of ongoing research on this. Okay, next to the next chapter, the training strategies. These apply to most neural networks, most sequence-to-sequence architectures. First of all, there's a training criterion like frame-wise cross entropy and chunking, generalized full-sum training, including CTC and the peaky behavior. Training methods like pre-training, visualization, data augmentation, and many others. And a couple of observations we made, like the training variance or amount of training epochs. So first, let's recap the frame-wise cross entropy. This is now for frame-wise models, for example, hybrid neural network hidden Markov models. In that case, you need a fixed given alignment. And alignment means that for every time frame, you have given the output label, some phoneme. So then the loss is defined like that. This is now just for one specific time frame. And the training pipeline for hybrid neural network model, the hidden Markov models, it's a bit complicated. First, you need to train a separate hidden Markov model with a Gaussian mixture model to generate the alignments. And only after you have done that, then you can use this alignment to train the neural network model. And this gets us the motivation for this work, the generalized full sum training, where the motivation is to be able to train from scratch without a given alignment. And also to aim for better performance, because you make use of any possible alignment, basically. So we call it full sum loss for hybrid neural network hidden Markov models, but it can also be defined for other models. Here it's the likelihood of the sequence, and then we plug in the definition of the model. And here we see that we have the sum over all possible alignments, and then the product over the time frames. This part here, these are the transition probabilities. They are usually fixed. Also, we have these exponents here. Then we have here the neural posteriors. This is the neural network. And we have some state priors. Compare that to the connectionless temporal classification, CTC loss. Now it's a discriminative sequence loss. And this is now very similar, actually. It also has here the sum over all possible alignments, but it only has this part of the neural network. So you can already see this is a special case of this. And this part here, the last part, is actually we don't really use in practice. There are several variants to this, like we can use the full sum, but we can also make a maximum approximation, so use maximum instead of the sum. The realignment we can do per mini batch, as we have seen in this loss, but then it can also be per epoch or fixed. We can, there are different topologies, hidden Markov model topologies, and maybe we can have an additional blank symbol. Then we can have transition probabilities, then the question on what type of neural network state posterior model you have, and the state prior model. So all of the training methods we discussed fall into this. The standard frame-wise cross entropy loss is fixed alignment, ignoring transition priors and training. CTC loss is full sum, realignment every mini batch, no transition, no priors. CTC topology is one state with an additional blank symbol. Our standard model does not have this blank. So we see that CTC is a simple special case in this scheme. So the contribution is identification of these relevant aspects and variants, and identification of CTC as a special case. To get to some experimental results, we'll compare it to frame-wise cross entropy training, where the frame-wise cross entropy used a fixed given alignment versus the full sum training. So one thing we noticed is that in the frame-wise cross entropy, our standard pipeline uses chunking, where we chunk up the sequence into parts, windows. This is possible because it's a frame-wise loss, but we cannot do it for sequence loss like full sum training. And we see that we lose a bit due to not using chunking. So that's one part where we lose. Further, so then our experience was full sum training was difficult to get to work at all, and we needed lots of tuning. And then when our result was like that, it was quite worse than the baseline. And we also calculated the frame error rate to the given alignment. We'd see that this is quite off from the given alignment. Then we had the idea to introduce a feed-forward network, because the idea was that the feed-forward network cannot really get the alignment much wrong, because it does not have context, so it must learn it converge into the right direction. And this turned out to be true. The convergence rate was much faster. Also, it improved quite a bit on the performance. And also the frame rate now drops quite a lot. But, so still, this does not reach the baseline performance. So contribution here is this implementation to really make it work. Lots of tricks in there. The feed-forward network is this idea, and we saw this effect of chunking. Okay, so another important observation we made during this work was when we trained with full sum without a prior, so setting gamma to 0, we observed that we get peaky behavior with silence. So to recap on peaky behavior, this is a well-known phenomena for CTC. So here you see CTC peaky outputs. This is a figure originally from Alex Graves. Here is the x-axis as the time axis. And on the y-axis, you see the neural network outputs as the probability outputs. And the different colors are different labels. And you see that the probability mass just focuses on single frames for the labels. And in all other frames, here you see the gray dotted line. This is the blank probability. So in most frames, the blank is 100% probability. So we categorized now different kinds of alignment behaviors of a model. So what we mean by meaningful alignment behavior is when the model actually outputs multiple frames of a phoneme with high probability. So here is the word ping, 3 phonemes. It would cover multiple frames here and then also here and here. And before and after there is silence. So the same with peaky behavior would look like that. It would focus it only on a single frame, the probability mass. Now you have to realize that there's a difference between blank and silence. Silence is defined that it can only occur before or after the word. So it means when you get peaky behavior with silence, it must put all the labels, the non-blank labels, right behind each other. So it looks like that. And this is exactly what we have actually observed when we do full sum training with our standard model, which just has silence but not blank. So we wanted to better understand why do we actually get peaky behavior. So here we constructed a very simple toy example. The target is just one label. So every possible alignment looks like that. There can be blank anywhere and then the label at some point. And we constructed an input such that this should be the optimal output alignment. So there's a number of blanks and then 2 times the number of labels and then again a number of blanks. And you see that this input really matches this, and there's a trivial, really simple solution for a neural network to map this input to this output. And we have a really simple, small feed-forward network with 2 parameters, which could trivially learn this. And because it has 2 parameters, we can plot it here for the loss. And we showed here the gradient curves. The middle point here, it's where we usually would start training. So this is initialized as uniform distribution. And we see that the gradient leads here to this regime. And this regime is exactly the peaky behavior regime. Whereas here would be the global optimum, where it would learn to really map this directly. So this is without prior. Further, we know that with prior it does not get peaky behavior. And here you see CTC now with prior. And here the convergence looks much different. Here, the gradient would directly lead to this global optimum without peaky behavior. So further, we wanted to study this effect of the ratio of the input length versus the output length. Again, it's a simple toy example. We look at the target sequence ABC. So we have 3 labels. Blank can occur anywhere in the alignment. And we construct the input such that this here would be the optimal alignment. And so here we can vary the length. We can upscale this. So by varying the length, we can get we can study this ratio. And here on this figure, now here it's the length, the t. And now, so first of all, in the red colors, we measure blank in the data set. So this is just about the data set. We see, so with here small t, we get around 40% blanks. This is summed over all possible alignments in the data set. And when we increase t, it gets higher, a bit over 50%. And then the blue, we train a very simple LSTM model with CTC, without prior, and we want to measure blank and measure the convergence time. So the solid line here is the amount of blank by the model. And what you see, interestingly, in the beginning, it does not output actually any blank at all. And then here is some tipping point where suddenly the model would output a lot of blank. So here it gets to peaky behavior, and here no blank at all. But it does not really reflect what the data set says. Further, what you see is the training convergence time. Here, lower is better. So what you see is that the lower this ratio is, the better your convergence rate is. So to summarize this part, full sum training without a prior, so gamma to 0, leads to peaky behavior. With prior, the situation is a bit different. Peaky behavior can be suboptimal in a couple of cases. What we have seen, when, for example, when there is no blank but only silence. For neural network models where you only have local context, like a feed-forward network, and when this ratio t times over s is big. There's several scientific contributions here. The observation of the peaky behavior for full sum loss, mathematical analysis and experimental analysis. So we really have proven this for a couple of cases. Fundamental understanding why and when peaky behavior occurs, understanding of the blank symbol, and understanding of feed-forward influence and the effect of this ratio. Okay, now to another training method. It's pre-training. The motivation is better and faster convergence. The idea is very simple. This has been done already before for feed-forward networks, but now we have adapted it. In this figure, you see it for BLSTMs. You start with a small network, here 1 layer only. You train that with your standard training criterion, your supervised training criterion. There's no special unsupervised training, pre-training here. And then after a while, you add a new layer, and you copy over the parameters of the first layer, and this new layer gets randomly initialized. And again, you train a bit with that, and you continue until at some point you reach your final model. And then you continue again training as normal. So this is the layer-wise construction. You grow the network in depth, and you copy the parameters. We further made several extensions to that. We also have started to grow in width, so the dimension. We started to do time downsampling scheduling. So we start with a higher time downsampling factor. We have seen from the previous slides that higher this would get you a lower ratio, and this improves convergence. And we also have applied it to Transformer. So the contributions are that we introduce a novel pre-training scheme for BLSTMs, for encoder-decoder models, for transformers, and the code and recipes are widely used now. To get to some results, it's basically as you expect, here for speech recognition and here for translation. With pre-training, here it's constantly better than without pre-training, here as well. And also with pre-training, the optimal depth is deeper. Here it's here, and here it would be here. here it's way down here, where the optimum without pre-training was only here. And it also allows you to train deeper models after all. And I think the only reason why this is worse than the optimum here is because there might be too much overfitting. Okay, to conclude this chapter, here we collected now a lot of different training methods, which we all studied, and we summarized the relative improvement. What we see here, overall, really the most relative improvement came from simple data augmentation, spec augment specifically, with 33% relative. Also, the regularization, dropout and N2 is really important, gets you big relative improvements. And a further thing is that the amount of training epochs actually also gets you quite a big improvement. But also all the others are still nice improvements. So we can say all of these are quite effective. Okay, to get to the next chapter, return. This was a huge part in this work actually, but I don't really go into detail now here in this talk. This is used for everything in the thesis, and it's used by many now in our group and at EPTech and also beyond. All the code is public, also most of the recipes are public, and you find it all on GitHub. So the goal was to combine simplicity, flexibility, and efficiency to use this framework for research and also for production. One thing we introduced was named dimensions. This allows you to write the configurations in a very robust way. This also allows for automatic batching, and this allows for optimizations, like you can reorder dimensions in your tensor. Further, we introduced automatic recurrent loop optimizations, which can make it quite more efficient in some cases. We introduced beam search in a very generic, flexible, and efficient way. This is part of the network itself. You can also use it for minimum expected word error training and many other things. Then we introduced a native implementation framework where you can write code with both CUDA and CPU support at the same time. We used that to write our native LSTM kernel and a couple of others. We also introduced the pre-training in a very flexible and generic way. Then we also have multi-GPU training. And there's also a big part is also the project management. First of all, we introduced continuous integration, and very importantly is the testing. So we introduced lots of tests for the framework. The scientific contributions are many novel technologies, all the implementation. This is now a widely used software, both in research and in production. Okay, to get to conclusions of this work, scientific achievements there. First of all, the practical and experimental improvements. All of these are widely used now. First, there's the baselines for BLSTM hybrid models. Then we were among the first to improve attention-based encoder-decoder models to reach state-of-the-art results. We have baselines for transformer attention-based encoder-decoder models, and of course the return software. A couple of novel contributions we made are, for example, all these baselines which did not exist before, so I think quite important contribution to the community. This analytical understanding of the peaky behavior, it's novel. Then the latent attention and segmental models, extended transducer model, and this equivalence of segmental and transducer model. Less successful in our work was this training from scratch with full sum. It does not reach the framework's cost entropy performance yet, so this is a negative result so far, but also this is still being worked on. And also this actually led us to this understanding of peaky behavior. Then the monotonicity and the attention models, this did not improve over the baselines. But now I would also say that we have better models, both transducer models and also better segmental models. So this is ongoing. To summarize results, the training methods actually in all of our work got us the biggest relative improvement. Also important, so this is including regularization and data augmentation specifically. Speckment got us over 33% relative improvement. Also important was neural network model types. Here, from going from feed-forward to LSTM got us 16% relative improvement. So for sequence-to-sequence architectures, this is still partly inconclusive. But this is still really an active field of research. But the relative improvements from one over the other is probably less than these improvements. So thank you for your attention.